All right, so just a reminder that quiz 6 on Thursday, it's going to cover section 11.8 to 11.10. So that's a quiz, but also remember that we have 6 quizzes in total, right? The one with the lowest grade will be dropped. So at the end, the grade from quizzes will only be calculated from your 5 highest quiz. So lowest quiz grade will be dropped. And I said last time I'm going to give you an optional homework, and I'm going to try to make the homework available today after this lecture at some point. If you're a little bit anxious about your grade now, so just keep in mind that there's a couple of ways that may make your overall grade a little bit better. All right, any other questions before we move on to today's material? Yeah, give it a try on them. At least read through the questions if you so at some point, right? Take a look at the questions. Don't wait until Thursday. Aiden, you probably tried a few questions. If you have any questions, like, give me a list of questions that you think will be difficult and just email them to me. I'll take a look at those ones. So here's a question. Asking if you don't get a good grade in optional homework, is that going to affect your grade in a bad way? No. So the optional homework grade, if you do well, great, right? If you don't do well, it's not going to have any penalty. It's not going to hurt your existing grade. All right. Well, I think some of you are working and take classes in the summer. That's great. I think you're doing really well this summer by doing both. Good job. Okay, so I'm gonna get started. And so recall that we talked about last Thursday, before we took the quiz. Well, if you have questions, definitely ask. Well, the material gets more difficult too, right? It's not just I intended to make the homework more difficult. It's sometimes the material gets more challenging and it reflects on the homework problems. Anyway, so do your best on the homework, like I said, and ask your questions. So let's go back to what we talked about last time. So recall we started 11.10 last time about Taylor and Maclaurin series. If you remember that for a given function, f of x, if we can write it as a Taylor series. So at this point, we're going to assume all the examples we come across, you can find the Taylor series and also the Maclaurin series representation. There are functions you cannot do that, but don't worry about that for now. So for f of x at a equals, at x equals some constant a, we can rewrite f of x and using the Taylor series formula, which is sigma n from 0 to infinity, f to the nth derivative. So that's n in a parentheses, with a being the input divided by n factorial, multiply with x minus a to the nth power. So that series, when we expand it, that will give us the Taylor series expansion. You can leave it in the sigma notation. This is perfectly fine. Or you can expand it as the first term will be the zeroth derivative just itself, f, with a being the input. Divided by 0 factorial is 1. X minus a to the 0th power is also 1, just f of a. And then the next term is 1n equals 1. So that will be the first derivative with a being the input divided by 1 factorial. Again, that's a 1. You don't have to write the 1 factorial there. And x minus a to the first power. The next term will be the second derivative when n equals 2. The second derivative with a being the input divided by 2 factorial, x minus a squared, and continues as we increase n. This is the Taylor series expansion. The Maclaurin expansion, it's a Taylor series, but with the a equals 0. So Maclaurin series is a Taylor series with a equals 0. It's a special case. And in this series, the f of x will equal to sigma n from equals 0 to infinity, same format. F to the nth derivative, the nth derivative of f with a, but here it's not just random a, it's a specific value 0 divided by n factorial. X minus a is x minus 0, but we can just write as x to the n. That's a Maclaurin series. And if you expand it, the first term will be f with 0 being the input instead of a different value. And then the next one will be the first derivative with 0 being the input divided by 1 factorial. And x minus a is x minus 0, but we can just write that as x. And then the second derivative with 0 being the input, 2 factorial, x squared, and it continues. So let me highlight the difference. The difference is that you have a f of a now become f of 0, f derivative of a become f derivative of 0, x minus a becomes x, and the second derivative, the input is 0, and then x minus a squared becomes x squared. That's the difference between Maclaurin series. So every time they say find the Maclaurin series for a function, you're gonna assume that it's a Taylor series expanded at a equals 0. That would be the important information. Even if it doesn't see it, will be at a equals 0. And then a couple special case, we saw it last time. So special functions, really not special, just like simple functions that they're going to show up a couple times. Hold on. I got to charge my laptop. It's going to die soon. Sorry, I'm going to pause the video and not to. I'm so sorry. Let me pause this for a sec. Okay, sorry, I'm back. Sorry about that. So there's a couple of special functions we talked about last time when we find the Maclaurin series for them. So the Maclaurin series for e to the x that one, if you remember, we found the series last time, which is just going to be 1 plus x plus, well, 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on, right? That one we can use the sigma notation. The first term is when n equals 0. The second term is n equals 1, n equals 2. So the sigma notation will be x to the n divided by n factorial, with n going from 0 to infinity. So that's the Maclaurin series for e to the x. It's sometimes it's benefit if you try to remember them.
What would you do if it's e to the negative x?
That's a good one. I'm going to ask you to hold on to that question. I believe there's another example I'm going to talk about today that has e to the negative x.
Perfect, because that was one of my homework questions.
Okay. Yes, I'll show you. There's a couple. Well, there's a shortcut and also sort of the traditional way. I'll show you that. Another one will be f of x. Oops. F of x equals cosine x. That one, when we expand it, we're going to end up with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. It's basically every term there has odd exponent and odd factorial in the, even exponent and the even factorial in the denominator. And this one, when written in a sigma notation, so that will be sigma n from 0 to infinity, negative 1 to the n, x to the, because it's all the exponents are even, so this is the n equals 0, this is the n equals 1, n equals 2. So the exponent will be 2 times n, 2n, right? That will give you even. And the denominator will be 2n factorial. Again, will be even. So that's cosine. And similarly, f of x equals sine x. So that will be, instead of beginning at 1, begin with x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And in sigma notation, that becomes n from 0 to infinity, negative 1 to the n again. Nope. Yep. This is the n equals 0. This is n equals 1. This is the n equals 2. So that will be x raised to the, when n equals 0, the exponent is 1. When n equals 1, the exponent is 3. When n equals 2, the exponent is 5. N equals 3. Sorry, yeah. N equals 2, the exponent is 5. When n equals 3, the exponent is 7. So all the exponents are 2 times the number n plus 1. They're odd numbers, so 2n plus 1 in the exponent, and then divide by 2n plus 1 factorial. So that's f of x equals sine. Now, here's another one that we didn't talk about. You could, I think that I have another example about finding them, but we might not have time to go over that. But the special one is f of x equals, let me just write it, we might use it, natural log of 1 plus x is equal to, let me write down the sigma directly, n from 1 to infinity of negative 1 to the n minus 1. Doesn't matter, that could be n plus 1. It's the same. X to the n divided by n. So this is a special case. The n began from 1, not a 0. All previous cases, the n began from 0. But for this one, for natural log, the n from 1. You can convert it to be from n from 0, but then all the exponents under the denominator n will be different. So those are the special cases. That will be more in the book. They make a list in the table. So see section 11.10 for more special cases. Well, what's the benefit of this, right? Why do we talk about those special functions? The benefit is that we can use them. So we can use those special cases to find out the Maclaurin series for other functions that may not be so straightforward. For example, Aiden asked earlier, what about e to the negative x, right? So for example, f of x equals e to the negative x. Let's see, we want to find the Maclaurin series. Right? And we already know that e to the x, let me just copy down what I had. So we know that e raised to the x will equal to sigma n from 0 to infinity x to the n divided by n factorial, right? That's what we know from what we did last time, also from the textbook. But we want to find the Maclaurin series for e to the negative x. Instead of going through the finding the f of 0, the derivative, like f of f prime, f double prime, f triple prime, instead of doing all that work and then come up with a formula, here we can take a shortcut. But before I do that, let me rewrite a couple of things. This is a e to the x. I'm going to rewrite as e to the capital X. Capital X is just a arbitrary x, right? And this will be capital X to the n. All the x in that equation, I'm changing it to capital X. I hope that's okay with you. But here, that one I can think about, it's a formula that I'm going to use, right? But here I have e to the negative x. So if I have, given f of x equals e to the negative x, I can think about the capital X that I wrote in purple in the box there. The capital X, when the example e to the negative x is equivalent to negative x, right? So the example e to the negative x, I can think about this part is just capital X. So I basically have e to the capital X form. And then I already know what this is. So I'm just going to use the idea that capital X equals e to the negative x. I'm going to substitute in there to figure out the Maclaurin series for e to the negative x. So that means e to the negative x, just like e to the capital X, that will equal to sigma n from 0 to infinity. And the capital X to the n power, I'm going to replace it with a negative x to the n's power. And then n factorial stays. So all I did is I sort of identified the part that's equivalent to capital X. In my example, that will be just negative x. And in the Maclaurin series, I took the part that's capital X and I replace it with this negative x, because negative x is equivalent to that capital X. Does that kind of make sense what I did there? So now I have this Maclaurin series for e to the negative x. I'm just going to rewrite it by splitting the negative one from the negative x. So I just have n from 0 to infinity, negative 1 to the n, x to the n divided by n factorial. So this will be my answer for e to the negative x. It's a lot quicker to find it this way. All right, any questions on what I did with this example by using the existing Maclaurin series to find out the one that I'm interested in? Where does the e go? In the In the Maclaurin series expansion, you don't have an E because it's a power series, right? We talked about the power series before, like when we first talked about it the first day. So you basically take some function, you write as Cn x to the power of n. So where the E, well, the E is included in here. So when you have an x value, you have different n. When you add all those together, that will give you a e to the negative x function. So why is the -1 at the end? Well, the -1, because here we have a e to the negative x, right? So here's a negative in the exponent. And that negative goes with the x when I plug into the sigma notation. And then the next step is I just separate them. We usually separate the -1 from other terms when we write sigma notation, when we write series. So all I did is I took the negative raised to the nth power, I separated from x, negative x to the nth power. So I sort of split -1, negative x to the nth power. I separate it as -1 to the n, x to the n. That's what I did. That's why I have a -1 at the end, coming from the -1 in the exponent of e. Any other questions? So this is for finding Maclaurin series. If you try to find Taylor series for e to the negative x at a given value, you cannot follow this directly because it will be slightly different. It's not exactly the same. Now, here's another exercise similar to this one. So this one, we're going to find Maclaurin series for the function f of x equals x squared cosine x. So this is the x squared times cosine x. If you don't, that's like, again, you can follow the traditional way by finding f at 0, finding f prime at 0, and f double prime at 0, and then I don't know what you talk about rate of change, radius of convergence. Okay, hold on to that question. And then from here, you can plug into the Maclaurin series expansion, f of 0 plus f prime of 0, 1 factorial x, f double prime of 0, 2 factorial x squared. You can do that. And then from there, then you can try to write down a sigma notation from there. That's possible, but it's just going to be a lot of work because when you take the derivative of f of x equals x squared cosine x, it's not, you're going to have to be very careful, right? Because you have to use a product rule there. Well, there's another way. So recall earlier we had cosine x when you write down the sigma notation. That's n from 0 to infinity. Right? And that will be -1 to the n, x to the 2n over 2n factorial. Right, that's what I wrote on the side here. So that's for cosine x. We already have cosine x, but here we're looking for the Maclaurin series for f of x equals x squared cosine x. Well, we know the series expansion for cosine x, even though we don't know the Maclaurin series for the product, but we know part of it. The other part is just x squared, right? So can we just put this in here, like a substitute for cosine x? You can do that. So that will become x squared times sigma n from 0 to infinity, -1 to the n, x to the 2n divided by 2n factorial. That is okay to do because in here, what you have is you summing up all the terms with x raised to a different power, right? Like you sum up like x to the 0, x to the square, x squared, x to the 4th, and so on. But if you multiply the sum by x squared, that's okay, basically distributing the x squared into every term there. So you can just substitute in there. So now that will become, I'm going to move the x squared inside the sigma notation and then combine it with this x to the 2n. So that will just be sigma n from 0 to infinity, it stays the same. -1 raised to the n doesn't change because it doesn't have x. 2n factorial doesn't change. Again, it doesn't have x. And then we have x squared, I move it inside, and I already had x to the 2n, but I'm going to multiply that with x squared. Those are the two terms that with x. Now I can combine them because that's just a product between two x terms with the same base. And if you remember that when you combine those two terms, and from 0 to infinity, -1 to the n, when you combine those two x terms, you basically add the exponent together. So that'll be x to the 2n plus 2 divided by 2n factorial. So that will be the Maclaurin series for f of x equals x squared cosine x. Any questions on that? So Chris had a question earlier about radius of convergence. I'm going to use this example, e to the negative x. So radius of convergence. There's a couple ways you can find it. The longer way will be using ratio test. So long way, it's a way that we always do in the past using ratio test. So for example, e to the negative x, we're just going to say L equals limit n from n goes to infinity of n plus 1 term, so that'd be -1 to the n plus 1, x to the n plus 1 divided by n plus 1 factorial. Divide by, I'm going to use this division, divide by -1 to the n, x to the n divided by n factorial. Keep absolute value sign there. So whenever you use a ratio test and the root test, remember what I said before, you have to use absolute value. Quite a few people lose points on that on the quiz. So that will be a limit. N goes to infinity. I'm going to just simplify this. So that will be -1 to the n times -1, x to the n times x, divided by n plus 1 factorial. And then we're going to multiply by n factorial divided by -1 to the n, x to the n. And I'm going to change the n plus 1 factorial to be n plus 1 times n factorial. And now I can cancel a few terms. So that will be limit n goes to infinity of -1 times x divided by n plus 1 absolute. Now I'm going to take the absolute value. So the -1 will become +1. For the denominator, I'm going to keep the absolute value. So that will be limit n goes to infinity 1 over n plus 1 times absolute value of x. And remember that we want this to be convergent, so that limit, the L, has to be less than 1. Otherwise, it's not going to be convergent, right? And how do we find out what x is there? So for what x value is this limit? Is this going to be less than 1? Well, let's take the limit as n goes to infinity. If n goes to infinity, the first absolute value, the 1 over n plus 1, that's going to approach 0, right? So this part, essentially, just when we take the limit, it becomes 0 times the absolute value of x. It's going to be less than 1. For what x value from there? Right? This should be, well, it doesn't matter what x is, as long as x is not infinity, right? So here we talk about finite x value. So for any x value, 0 times the x will always be 0. So that's always going to be less than 1. So for all x value, the 0 times absolute value of x is always going to be less than 1. So all x value works here. Therefore, the radius of convergence for this example, it's just going to be r equals infinity. It's from 0 to infinity, any number will work. So that's a radius of convergence for this example. If you don't know how to find radius of convergence, it's always good to try this ratio test to find the L, and from there set it less than 1 at the end. That will always work. But if you have another expression that you can, I'm going to put it here. If you can end up with x minus a absolute value less than r there, if you have that expression at some point, the r value will be radius of convergence. But in this example that I work with, I couldn't end up with that expression because the left side of the inequality is going to be 0. So 0 less than 1, which is always true for any x. Therefore, the radius of convergence is infinity. Okay, that's a very good question. I'm sure you're going to run into more questions on the homework problems, which I'm going to talk more about it on Wednesday. That's the second way to find it. Okay. But for now, that would be a good approach. All right, is this the type of stuff you learn more about in multi-D calc? Yeah, I would say some of this you're going to have to use, but though actually I'm going to stop there because I don't know exactly what's in that class. All right, here's another exercise on this type. So find Maclaurin series for the function natural log 1 plus x cubed. Again, this one you could just follow the formula for Maclaurin series, find each term, taking the derivative, find each term, and then put into the general formula. That's okay. But since earlier I wrote down the special case, so recall earlier I wrote, what did I say, the natural log? So we have f of x equals natural log of 1 plus x, and that's equal to this Maclaurin series. So maybe we can use it. So natural log of 1 plus x, that's equal to sigma n from 1 to infinity, -1 to the n minus 1, x to the n over n. I'm not going to ask you to memorize this, but it's in the book if you need it. So this one, again, this is natural log of 1 plus x. I'm going to change the x into capital X. It's the same. It doesn't change anything. It just means that, it's different from a lowercase x in the given question, right? So if you have natural log 1 plus capital X, then the Maclaurin series is in this form. Well, here we are interested in natural log of 1 plus x cubed. Can we follow the same pattern? Can we treat x cubed? Can we treat it as capital X, like the equation above? Yes, why not, right? If x cubed equals capital X, we end up exactly the same form, 1 plus capital X. So we can just say capital X equals x cubed. And that's the left-hand side. The right-hand side will be the same. So that will be sigma from n equals 1 to infinity, -1 to the n minus 1. It doesn't depend on x. Times, now it used to be capital X raised to the n, but capital X is x cubed. That will be x cubed raised to the power of n. And divide by n doesn't change. It's just n. So that will be the Maclaurin series for natural log of 1 plus x cubed. And we can simplify this by just simplify as much as possible. So that will be sigma n from 1 to infinity. It's a whole thing over n, but it doesn't matter which part you underneath. Right now we can put it over the whole thing, but it doesn't really matter. I'll just put it over underneath the second one. X to the 3n divided by n. So that will be the Maclaurin series for this case. So this method works really well and really quickly because, some of it we already know, right? Sort of like the general form we already know. We just substitute it for the x part. So for homework, if there's some questions you can apply this trick, definitely apply it. That will save you some time. I don't know how helpful this special series are, but if it is, if you feel like, oh, looks like we can take the shortcut, definitely use it. Right, but doesn't mean every question you can follow them, right? So that works for Maclaurin series. In the book, like I said earlier, there will be more series like that. But for now, I want to talk about a couple of special cases. Not special case, just more exercise about finding Taylor series. For, let's see, the first one I have is finding Taylor series for f of x equals x cubed minus x squared plus 6 at x equals 3. So that's an a value. We're going to expand this function using Taylor series at x equals 3. This is the a value, a equals 3. And the Taylor series f of x equals sigma f to the nth derivative with a divided by n factorial x minus a to the n, and from 0 to infinity. And if you expand it, become f of a plus f prime a 1 factorial x minus a, and then f second, excuse me, second derivative a 2 factorial x minus a squared, and it continues. Right. So if you look at each term there, we need to know what f of a is, and we need to know the derivative with a in it input. So let's just make a list. So f of x we know is x cubed minus x squared plus 6 given. And from there, we can find out that f of 3, because a is 3, which is equal to just plugging 3 into the function. So it'll be 3 cubed minus 3 squared plus 6. 3 cubed is 27 minus 3 squared. That's minus 9. It's 18 plus 6, 24. And then f prime, the first derivative, we just take the derivative. Hopefully we feel comfortable by now. So that will be 3x squared minus 2x plus 0. And we also need to find the first derivative evaluated at a, 3. So that will be 3 times 3 squared minus 2 times 3. So that will be 27 minus 6, right? 21. And then we need to find the second derivative. So that will be 6, 2 times 3 is 6x minus 2. And then we can evaluate the second derivative as 3. So that will be 18 minus 2, that's 16. And then continue this, the third derivative, it's just going to be 6. There's no x left after we take the derivative. So the one we plug in 3 for x, there's no way to put it. It's just going to be 6. Right. So Frank has a good point. So if we continue this, the fourth derivative, I'm going to use this notation. That will be 0. There's no x left. So the fourth derivative at 3 will be 0. And what about the fifth derivative? Well, if we take derivative of 0, we're still going to end up with 0, right? So if we continue that, the 0 just repeats. So for all derivative greater than or equal to 4, we get 0. So here's also 0. Which is not a bad thing, even though it looks like, you know, weird case, weird example, but it's not a bad thing. So if we apply into the formula, so f of x, right? This is a Taylor series expansion expanded. This is not expanded. If we plug into the expanded formula, so that will be f of 3, 24, plus f prime of 3. So that's a 21 over 1 factorial, just 1. You don't even have to write the 1 factorial. And then x minus 3, right? X minus a, plus the second derivative, which is 16 over 2 factorial, x minus a, x minus 3 squared, plus 6 divided by 3 factorial, x minus 3 cubed. And then the next term, the f to the fourth derivative, that's just going to be 0 times some. So it'll be 0 over 4 factorial, x minus 4, x minus 3 to the fourth power, and then 0, you know, and so on. They all become 0. So you don't have any terms after the x minus 3 cubed. So this is the Taylor series expansion of f of x at x equals 3. I would ask you to find some time and plot them, see what you end up with. See what you notice when you plot those functions. So you plot this expansion and also the one that's given. and compare them, see what you notice, especially at x equals 3. So that's one example. Any questions on that? The next example I have is find Taylor series expansion for f of x equals 1 over x squared at x equals -1. So I'm going to follow the same pattern. So I'm going to write down f of x first, because again, I need to know the f at -1, the f prime at -1, and all those terms, right? So f of x equals 1 over x squared. You can write as negative x to the positive x to the -2 to make it easy to take the derivative. And the f prime of x is equal to -2 x to the -3. So that's a -2 over x to the -3. I mean, over x cubed. Sorry, not over x to the -3. And then if the second derivative, if we take the derivative of the previous one, so that will be -2 times -3 over x to the times x to the -4. So that will be, I'm going to write it as 3 times 2 divided by x to the 4th power. And then the third derivative, which is going to be -2 times -3 times -4 times x to the -5. So that will be, I'm going to write as a 4 times 3 times 2, but with a negative, because I get 3 negative, I end up with 1 negative, divided by x to the 5th. And then that pattern continues. And I need to know that here x equals -1, that's a value. So a equals -1. So I'm going to put in there. So f of -1 is just 1 over -1 squared. That's a positive 1. And f prime of -1. So if we take a -1, put in there, so we get -2 over -1 cubed. -1 cubed is -1, so we get +2. And there's a second derivative at -1. So that would be 3 times 2 divided by -1 to the 4th power, which is +1. So that will be 3 times 2. You can write that as 3 factorial, right? 3 times 2 times 1, which is 3 factorial. The 2 above, you can write as 2 times 1, 2 factorial if you like. But if you don't see that pattern, that's okay for now. And if we continue this, the third derivative evaluated at -1, so that will be -4 times 3 times 2 divided by -1 to the 5th power, that's a -1. So we cancel with the negative above, so we get 4 times 3 times 2 is the same thing as 4 times 3 times 2 times 1. So that's a 4 factorial. Right? So now we can take this and put into the Taylor series formula, but note that before we do that, note that if we have nth derivative evaluated at -1, we can figure out that by just looking at the pattern, if you have 0th derivative, the original function, you get 1, you can write as a 1 factorial. If you have 1, the first derivative, that will become 2 factorial, which is 2 times 1. If you have a second derivative, you get 3 factorial. You get third derivative, you get 4 factorial. So if you have nth derivative, evaluate at -1 following the pattern, we should end up with n plus 1 factorial. So now we can put into the Taylor series. Again, you can put in the expanded form or you can put in the sigma notation. So that will be f of x equals, if you put it in the expanded form, so it will be f of -1, that's f of a 1, plus 2 over 1 factorial x minus -1, which is x plus 1, plus the second derivative, which is 3 factorial over 2 factorial times x plus 1, x minus -1 squared. And then we can continue this, so that will be 4 factorial over 3 factorial x minus -1 x plus 1 cubed, and so on. And you can simplify this because 2 divided by 1 factorial, that's like a 2, just 2. 3 factorial over 2 factorial, so this part becomes 2, this part just becomes 3, this part becomes 4. So there you have a pattern. You can use sigma notation, or you can put it directly into the sigma notation, which says this part is going to be f to the nth derivative with a input. We know that's n plus 1 factorial. We already found it. So this is an n plus 1 factorial. And then divide by n factorial, that's what's in the formula. And then x minus a x plus 1 raised to the n directly. So it works really well in this example. And now we can sort of simplify n plus 1 factorial divided by n factorial. That should just, you should be familiar with it at this point. So that's an n plus 1 times n factorial divided by n factorial. So that cancels, give you n plus 1. So we just end up with sigma n from 0 to infinity n plus 1 times x plus 1 raised to the n. So there's a couple ways. Even if you put in the expanded form, you can still observe the pattern, right? Like the pattern going from 1 plus, so let me maybe move this down a little bit. So the pattern is the terms going with, allow me to move, fine. So the pattern is it going from 1 plus 2x plus 1 plus 3x plus 1 squared plus 4x plus 1 cubed. So this is like an n from equals 0. This is the n equals 1. This is the n equals 2, n equals 3, and continues. So that will be just sigma. Don't look at the 0 term, look at it later. But n, the equals 1 term, you get 2, n equals 2, you get 3, n equals 3, you get 4. So it looks like that's the n plus 1. And then you always have x plus 1 raised to some power. The power n equals 1, you get 1, n equals 2, the exponent is 2, n equals 3, the exponent is 3. So to the n, and from 0 to infinity. And then you can check, see if it gives you the first term. If n equals 0, we got 1 times 1 equals 1. So that works. It's the same thing as if we plug into the sigma notation directly.
Why is there no factorial sign on the 2 there?
I didn't write it. You could write as a, you could, so I didn't write the 2 factorial, the factorial notation. You could put it there because it's just 2. You can think about it as 2 times 1, right? So that's a 2 factorial. You can think about it in that way. The 1 here, you can also think about as a 1 factorial over 0 factorial because both are 1. 1 factorial is 1, 0 factorial is also 1 by definition. So you can just think about it as 1 factorial over 0 factorial. That way it follows a pattern. For me, I'm not saying it always works. For me, when I want to take a multiple terms and then try to write it as a sigma notation, I usually don't look at the first term because the first term usually it's just a number, just a constant, right? It doesn't tell you much. I usually look at the second, third, and the fourth term because those terms have an X in them. You can try to sort of come up with a formula easily from them, and then at the end, just double check, make sure it gives you the first term when n equals 0.
What if instead of writing like 3 factorial, 4 factorial, you actually just wrote out the numbers?
If you write as numbers, it's a little bit difficult to see the pattern at some point, because if you have like a 6 and 24, sometimes if they cancel out nicely, you can still see the pattern, right? But in some cases they don't cancel, so it's difficult to see the pattern. So I would recommend that when you in problem like this, when you find the derivative, pay attention to what the constants, like when I'm taking the derivative here, I notice that not from the first derivative, right? That's not obvious, but from the second derivative, I notice that I take the previous number -2 and I multiply with the new number -3. So it gives me something like this. So that shows me that, oh, it's going to be the constant is going to be a product of 2 numbers, right? Just 2 integers, 3 times 2. And then when I take the next derivative, I get -2 times -3 times -4. It looks like it just multiplied by the next integer that's negative. So that's sort of indicating that's like a factorial in the pattern. All right, let me go through another example. So the next example is find Taylor series for f of x equals natural log of x, just natural log of x, at x equals 2. This is the a value 2. And again, I'm going to try to do the same thing. So take the derivative. F of x given is natural log of x. The first derivative would be just 1 over x. You can write it as x to the -1. The next derivative, the second derivative, will be derivative of the previous one. So that'll be -1 times x to the -2, which is -1 over x squared. And then the third derivative, which would be take the derivative again. So that would be -1 times -2 x to the -3, right? So that would be, again, so here, when I see something like this, because each derivative after this just multiply by the exponent. So the next derivative will have -1 times -2 times -3. So that's an indication of this factorial. So in this case, in this example, I'm going to leave them the way it is. I'm going to write as 2 times 1 over x cubed, or 2 factorial. And then the fourth derivative will be -1, -2, -3 times x to the -4. So that will be 3 times 2 times 1 with a negative, divided by x to the 4th power. And now I'm going to plug in x equals 2. So f of 2, so that will be natural log of 2, right? And the f prime of 2, so that will be just 1/2, 1 over x, 1/2. And then the second derivative evaluate at 2, so that will be negative 1 over 2 squared. The next term, the third derivative evaluated at 2, so that will be 2 times 1 divided by 2 cubed. You can think of it as 2 factorial or just 2 times 1. It's up to you. And then the next term will be the fourth derivative evaluated at 2, so that will be negative 3 factorial over x 2 to the 4, right? So this is not obvious, but looks like that's a pattern, right? What about f to the nth derivative evaluated at 2? Well, you got to be very careful here, because here, not only you have 1/2, 1 over 2 squared, 1 over 2 cubed, and 1 over 2 to the 4th, but you also have a negative 1 that alternates, right? The second derivative, you have negative. The fourth derivative, it's also negative. So you have to be very careful with the alternating sign. But before, maybe I'll show you this. The first term, not much we can do, just natural log of 2 is not even in the pattern, right? So let's just put it aside. And this is the f to the first derivative. So that's just 1/2. The second, so that one, I'm going to leave it for now because I may not get to the correct form, but the second derivative, I'm going to write it as a negative 1 times 1 over 2 squared, right? The next term, it's going to be positive 1 times 2 factorial divided by 2 cubed. Now the positive one, if you want to use something with negative 1, you can write as a negative 1 squared. If you just try to follow the pattern to make them all have negative 1. And then the fourth derivative, so that will be negative 1 again, times 3 factorial over 2 to the 4th. And maybe now go back about the first derivative, you can write as negative 1, I don't know, maybe negative 1 to the 0th derivative. That will give you positive 1 because we want it to be positive and the 1/2. If you want to add negative 1 to all the terms. And this one, I'm not writing it following the pattern. So this is just negative 1. We can make it negative 1 cubed if you like, to make the pattern more obvious. Anyway, we just want the negative 1 to alternate, right? So now we can try to write down the pattern f to the nth derivative evaluate at 2. So that will be, looks like it's negative 1. The fourth derivative have negative 1 cubed. Third derivative have negative 1 squared. Second derivative have negative 1 to the first power. So it looks like that's just negative 1 to the n minus 1. And then times fourth derivative, we got 3 factorial. Third derivative, we got 2 factorial. So it looks like that's going to be 1 less. So that'd be n minus 1 factorial. And what about the denominator? The fourth derivative, I get 2 to the 4. Third derivative, I get 2 cubed. So that seems to be the same. So that'll be 2 to the n. So this will be the sort of the expression for f to the nth derivative. It takes a lot of practice to be able to write down those, like follow the pattern, try to write down the sort of the formula. Sometimes you cannot do that. Sometimes you can. But be careful here, the first term, the very first term, f of 2 equals natural log of 2, that I cannot write that. Right? So this is the n equals 0. This is the n equals 1, n equals 2, n equals 3, n equals 4. the n equals 0 case, this is the n equals n, obviously. But the n equals 0 is a special case. I cannot write it using this pattern. Nevertheless, we can still find the formula. So the Taylor series expansion says it going from 0 to infinity of f to the nth derivative of a is 2 in this case, divided by n factorial x minus 2 to the n, right? That's going from 0 to infinity. I could separate that into just n equals 0 alone. So that would be just natural log of 2. So that's a f of 2, n equals 0 case, plus sigma n from 1 to infinity. So all the rest terms, I can keep it in the sigma notation. So that will be f to the nth of 2. So that will be -1 to the n minus 1, n minus 1 factorial divided by n factorial. And then we have 2 to the n times x minus 2 to the n. So that's a Taylor series expansion. You can try to simplify a little bit. The n minus 1 factorial, the denominator n factorial, n minus 1 factorial divided by n factorial. So that will be n minus 1 factorial divided by n times n minus 1 factorial. So those cancels give you n in the denominator. So just end up with natural log of 2 plus sigma n from 1 to infinity, -1 to the n minus 1 divided by n times 2 to the n, and then multiplied by x minus 2 to the n. So that will be in the sigma notation. If you feel like, this is just very challenging for you, it's a top sync box, not the answer. This is not final answer. The one that I put a star next to it, that expression is just going to be this part. It's only part of the Taylor series. So that's that in the box there, it's just going to be f to the nth derivative of 2 when n is from 1, 2, 3, 4. You have to take that expression, put into the sigma notation, and then simplify. This is the final answer here. If you feel like you just cannot handle this sigma notation, by sort of like if what I did was confusing to you, right? You can always like expand it, find the expanded form, which is f of 2, natural log of 2, plus f prime. Remember, f prime is just 1/2. So that will be a 1/2 divided by 1 factorial x minus 2 to the first power. This is the n equals 1. Plus n equals 2 term, so that will be f to the second derivative. So that would be -1 over 2 squared. Divided by 2 factorial x minus 2 squared. And then the third derivative, which is 2 factorial over 2 cubed. I didn't expand everything, so that will be 2 factorial over 2 cubed divided by 3 factorial x minus 2 cubed. And I just didn't expand those, didn't simplify them. If you simplify each of the coefficient terms, you might be able to observe the pattern there after you simplify them. It may not be that straightforward to observe a pattern that looks like this. So I would say if it's possible for you to come up with a formula for f to the nth derivative evaluate A, if it's possible to do that when you try to find those terms, f prime of A, f double prime of A, and so on. If you can observe a pattern, try to write down the general formula for the pattern. That way you can just directly put into this Taylor series sigma notation. Right? If you cannot do that, you can always go to the expanded formula, try to write down the expanded form, and from there, do your best to write down the sigma notation. If it's just too challenging, at least make a list of those terms. Write down, like, I don't know, I write down 4 terms. You can write down 4 terms as well and then leave it there. All right. Any other questions about this example? It's not as easy as the previous one because here n equals 0 is a special value, right? It doesn't fit in the pattern. So you kind of have to put it aside when you write down the Taylor series. Now I have about 25 minutes, so I'm going to go through the last part of what I was planning on talking about. The last part is called binomial expansion, binomial series, which is sort of like the power series, but it's for special type of functions. So let me write down the definition first. So binomial series. So if k, some constant k, is a real number, could be any, just a real number, and absolute value of x is less than 1, then I'm going to use capital X because I'm going to use substitution later. So absolute value of capital X is less than 1, then 1 plus capital X to the k's power, this function f of x, capital X. If f of x is in this form, 1 plus x to the k, then we can write down the series expansion. So that will be sigma n from 0 to infinity, parentheses, k n. I don't know if you've seen this before, you probably have, capital X to the n. Again, let me erase all the capital X. I'm going to use purple color there to show you to show it's different. So that's sort of, you can think about this as a formula for binomial series for function like this. Like for example, if you have 1 plus x to the 5th power, right? You can expand it in this form. Is that k divided by n? No, let me see. This is called k choose n. It's just a term. It just well, way we write it. So mathematically, k n. So there's no line between them. Just k n in parentheses. This is equal to k factorial. You're probably seeing it in high school. Divided by n factorial times in the denominator times k minus n factorial. That's what this expansion is. But here in this example, so let me put it here if I can move it. No, I cannot move it. Okay, I can move it. So this part is equal to this. It's also, you can expand it. It eventually become k minus 1, k minus 2, multiply dot dot dot. It's all multiplication. K minus n plus 1 divided by n factorial. That's what you end up with when you expand it. Now, let me use a simple example to make sense of this notation. For example, if I have so this is I'm going to erase this in a second. So if k equals 5, n equals 2, or like k equals 7 for the math. K equals 7, n equals 2, for example. Then k n in a parenthesis. So k choose n, so that will become 7 choose 2. So that will be 7 factorial divided by 2 factorial times 7 minus 2 factorial. So that's a 5 factorial. So this is a 7 factorial over 2 factorial times 5 factorial. That's what that is. And if you expand the numerator, so that will become 7 times 6 times 5 times 4 times 3, 2, 1. Divided by 2 factorial, I'm going to leave it. And the 5 factorial is 5 times 4 times 3 times 2 times 1. And they all cancel. So basically every term in the 5 factorial, or the 7 minus 2 factorial, right? So basically when we expand this part, all those terms, so after we expand it, all the term k minus n factorial will cancel. Always. That's why we only end up with n factorial in the denominator. So if that cancels, what do we have? We have 7 times 6 over 2 factorial. So n equals 2, remember, right? N equals 2k7. So you can think about this as like a k times k minus 2 plus 1, which is k minus 1, divided by 2 factorial. So that's sort of following this pattern here. K times k minus 1 and so on, all the way to k minus n plus 1 divided by 2 factorial. But for this, I'm just going to write down a few special ones. So for the binomial series, kn is this expansion, expansion. A special case, k0 is always going to be 1. K1 is just going to be k. Those are special case. K2 is just going to be k. K minus 1 over 2 factorial. I probably should say you can add a 1 factorial there, but you don't need to. You can sort of remember those special cases, like, if, you know, at least know where to look, you know, where to find them, right? And then case 3, so that will be k minus 1, k minus 2, divided by 3 factorial. And the pattern continues, right? If you have k4, so you just have another term in the numerator and divide by 4 factorial. So those are like sort of the special ones that you can use directly if you just want to expand them. I think when you study permutations in high school, you probably come across this. I could be wrong there. But anyway, so let me give you one example on this. So the example, I've never seen it before. Okay. Well, that's perfectly fine if you haven't seen it before. I just want to explain what that is. Good to know. So yeah, so that's what the K, with N below it and the parentheses, that's what I meant. So this example I'm giving you is, so we're going to find binomial series for the function f of x equals square root of 9 minus x. So square root of 9 minus x is the one that I want to expand using binomial series. Even though it doesn't look like the given one, right? I'm going to just copy down what I wrote earlier. This given formula, right? It's like 1 plus x to the k, but the one I'm given, it doesn't look like it. Well, we can manipulate this example into 1 plus x to the k. This one we know that's a sigma n from 0 to infinity, kn capital X to the n, right? That's sort of the formula. We can take the given one and try to manipulate. It looks like a 1 plus x to the k. We can try to do that. Then we can just sort of put into the formula directly. Okay. So let me try to do the manipulation first. So we're going to take square root of 9 minus x. I'm going to make it into 1 plus some capital X form, right? Raised to the k power, raised to some power. So what do we do? Well, the first thing I'm going to do is that I'm going to rewrite the underneath the square root. I'm going to make it look like a 1 plus something. So that will be square root 9. I don't like 9, so I'm going to factor out the 9. So 9 times 1 minus x over 9. Right? And I'm going to continue this. So that becomes square root of 9. I'm going to take it out. So that becomes 3 square root 1 minus x over 9. Looks close. We get a 1 there. But we want 1 plus. So that will be 3 square root 1 plus negative x over 9. So that's pretty good, right? We get 1 plus capital X. With this part, you can think about it's just capital X. But it's underneath the square root. Can we rewrite it? Yep, we can write as we can write this as 3. Instead of square root, I'm going to write as 1 plus negative x over 9, but in a parentheses, raised to the positive half exponent. So the k is half. So k is equal to half. So this is the k value. And this part, I'll use a different color. So this is, again, this is capital X. And this is the k value, 1/2. So what about the 3 in front of it? Well, that one we can just leave it, don't worry about the 3, just a constant. Let's just put it aside. Let's focus on this part alone. So I'm going to rewrite it on the left here. So the function given f of x equals square root of 9 minus x. I can write this as 3 times 1 plus negative x over 9 raised to the 1/2. So that's like 1 plus capital X to the k form if we kind of ignore the 3 on the left. So let's follow the pattern here. So let's follow this pattern to rewrite this part. So that will be 3 times sigma n from 0 to infinity, parentheses k. What is k? K is 1/2. Right? What about n? Well, n is just n for now. And then capital X is negative x over 9 raised to the n. right? That's just put in directly into the binomial series general formula. And then the rest we can try to expand it. It's so this term, be careful, n goes from 0 to 1 to 2 and so on. So if we want to expand this, so we get 3 outside, just leave it. I'm going to add a big bracket to distinguish. So the first term will be 1/2, choose 0. And then put 0 there, so we get negative x over 9 to the 0, it's 1. Plus, let's put 1 there, so we get 1/2, choose 1. And then we have negative x over 9 to the first power. And now n equals 2, so that will be 1/2, choose 2, negative x over 9 squared. And then continue this. I'm going to do one more term, then I'm going to stop. 1/2 over, choose 3, negative x over 9 cubed. Because the term's getting bigger. It doesn't make any sense to keep adding more terms. We know they're there. So what do we have? We get 3 bracket 1/2, choose 0. Remember earlier I wrote k choose 0 is always 1. So even if you have 1/2, choose 0, you still have 1. So this is just going to be 1 plus 1/2, choose 1. So that's a k choose 1. That's a k over 1 factorial, just k. So in this case, this term is just 1/2. Times negative x to the over 9. Plus, what about 1/2, choose 2? That is, oops, this part is going to be k times k minus 1 over 2 factorial, but k is 1/2, so you get 1/2 times 1/2 minus 1 divided by 2 factorial, and then times negative x over 9 squared. Plus, how about the next term? So that will be 1/2 times 1/2 minus 1 times 1/2 minus 2 divided by 3 factorial, negative x over 9 cubed, and it continues. So the rest
Just leave it at the second line, or would you get points marked off for that?
If you leave it at second line here.
Second to last, sorry.
Second to last, over here. Yes, because for a problem like this, if you want to leave it in an expanded form, like have a few terms added, like that's what I'm trying to do, just like have 4 terms added together. You have to simplify the constants, at least try to simplify as much as you can. If you have factorials, you can leave them, right? But if you have like 1/2 times something, you might want to multiply them together. Because it's already expanded, so you want to give us, give as much value as, as direct value as possible. So that will be, let me just finish simplifying this. That was a good question, Sam. So that will be 3 times 1 plus, this is a 1/2 times negative x over 9. So that's a negative, not positive, x over 18. And then plus 1/2 times 1/2 minus 1, that's a 1/2 times a negative 1/2, right? So that's a negative 1/4. But then you already have 2 factorial, so that's a 2 in the denominator. And then times negative x squared, just x squared, divided by 9 squared is 81. As you can see, the value already getting really big. You probably need to use a calculator to multiply the denominator together. And the plus, the numerator for the next term, 1/2 times negative 1/2 times negative 3/2 divided by 3 factorial. And then you have 9 cubed, then you have negative x cubed. 9 cubed, I don't know what it is. It's a very large number. So I'm not even going to bother to show you how to do it by hand because that's just going to take a while. Anyway, so my point is that if you want to expand it, write it in an expanded form, you should give more more direct values. So now distribute the 3 in there. So that will be 3 minus x over 6. The next term, I don't know what it is, to be honest. I'm just going to copy it from here. So that's negative x squared over 216. And the next term, I don't know. I'm just going to leave it there. So because the next term, the denominator got a lot bigger because it's a 3 factorial times 9 cubed. Then you have 2, 2, 2, have 8 in the numerator that will come down to the denominator. But with a calculator, you should be okay. Sorry, x squared. The next term is x cubed. I don't know what it is. But the sort of the key point for this question is that if you have something that doesn't look like the direct form of binomial, like 1 plus x to the k, you can always manipulate it so that try to make it look like 1 plus x to the k. And then you figure out what the capital X is corresponding to, what the k value is, and then sort of put it in there directly. Yes, you could leave the factorial in the denominator if you want, like leave the 2 factorial, the 3 factorial, that's okay. It turns out that in this case, it doesn't help you much because it's the other terms that has a really, really big denominator value, like 9 cubed, right? That's a very large value in the denominator. And here you have a 9 squared, and then you have a 4 there. So when you multiply them together, they're already very big. But definitely, when you have a problem like this on the homework, definitely practice to expand this. Sorry, didn't mean to make it worse. To expand this k choose n form, because that would be a good practice. You know, I just expand it by plugging n directly, and then find each one of them. Okay, I'm done here for today. And tomorrow, hopefully we're going to finish everything so that on Thursday we could have a short day. We have a quiz on Thursday. If you have homework questions, ask them on Thursday as well. Anything we talk about tomorrow, it's not going to be on the quiz. So today is the last, like everything we talk about today could be on the quiz, right? Taylor series, Maclaurin series, those could be on the quiz. And then keep in mind that, it's only 30 minutes quiz. So we're not going to give you very difficult questions, but you do need to review, right? Review the material before the quiz. All right, I'm going to stop talking. So I'll see you guys on Wednesday or office hour tomorrow. Take care.